In this video, we're going to look at transformations. So previously, when you learned about linear regression, one of the things that we learned was really important was always check the assumptions, to make sure that, you don't need to tweak the model, that there's nothing of real concern here. And we usually would do that through diagnostic plots. And in particular, we were usually looking at the residuals. And our whole goal here was to figure out whether or not those model assumptions had been violated. What we didn't spend too much time doing was talking about, well, if those assumptions are violated, what options do you have? And to a pretty big extent, that's really going to be the purpose of this course. So you've violated your assumptions of linear regression. What do you do next? And there are multiple ways that those assumptions could be violated. So generally speaking, there are going to be three options to you. You can transform some of the variables, and you touched on some of that in the linear regression course. You can fit a more flexible model. So we also touched on that some, and we'll just briefly discuss it here. Or you could use a different method. And using a different method is really going to be, to a large extent, what this entire course is focused on. But for just this set of notes, we are going to focus mainly on the first option and then just mention the second two. All right, so we're going to focus here and just talk about simple linear regression, but the things that we talk about could easily be extended to multiple regression, and we're really going to focus on transforming variables. So since we're going to focus on simple linear regression, there's only two variables. You've got a single predictor and you've got a single response. And so we're going to start out by looking at the predictor variable and what happens if we transform the predictor variable and why we should transform the predictor variable. And then we're going to look also at transformation of the response variable. All right, so when there's a lack of linear trend in the data, it may be appropriate to transform the predictor. And so I just kind of want to highlight this here, that transforming the x values or those predictor values are appropriate when non-linearity is the problem. So what you're going to see here is the type of transformation you perform is going to be dependent on the type of problem. So if non-linearity is the issue, then it's appropriate to transform the x values. So if you violate independence, normality, or equal variances, then you're going to have to do some other things as well. And so kind of a note here is, though it may be necessary to correct nonlinearity before you assess the normality and equal variance assumption. And then also, while some assumptions may appear to hold prior to applying the transformation, they may no longer hold after the transformation is applied. So what you're going to find here is we really have this iterative process. So just because you checked let's say you check all of the assumptions and the only one that was violated was the linearity, so you perform this transformation and you recheck linearity alone, that doesn't mean you're done. Anytime that you do any kind of transformation, you want to go back and reassess all of the assumptions. All right, so let's look at an example here. We're just going to look at a small data set. So we're going to look at data from a memory retention experiment where there were 13 subjects and they were asked to memorize a list of disconnected items. The subjects were then asked to recall the items at various times up to a week later. Each subject was asked to recall only one time. So notice here, we don't have a time series. They're not recalling multiple times. It was just they had a large pool of people and they took, some of those people recalled at a certain time, a different group recalled it a second time, and so on. And so our two variables we're interested in here are the proportion of times that the person correctly recalled, and then x is going to be the time in minutes since the list was originally memorized. And so we have a plot here, and one thing to notice here is we're not going to violate our independence since each person is only recalling the words once. We're probably good with our independence assumption, but let's look at some of our other diagnostic plots. So the very first thing I do want to look at here is just the scatter plot. And we can see, very quickly looking at the scatter plot, that is not in a straight line. So we know right off the bat, we're going to have an issue there because that's obviously curved. And then we could look at some of the other diagnostic plots here. Looking at the normal QQ plot, it looks like we have normality of the residuals. But since up here we know, we have violated that linearity assumption, we could also look here at the residuals versus the fitted, that we don't have that random scatter. So even more evidence that we have violated that linearity assumption. Something is not, not doing well here. Our model, this is not a good fit. So even though these look normal, you might be tempted to say, oh, well, let's fix the linearity assumption, then we're good to go. That's not the case. Since we have violated linearity, we really can't trust this normal QQ plot. Yes, those residuals look normal, but it doesn't really matter because we didn't have a good fit of the model. All right, so instead, let's look at a transformation of that predictor variable and see what we end up with. So the logarithmic transformation is the most common and most useful data transformation available. We're going to see it here with both the predicted, we'll also see it later on with the response, and it's usually denoted as ln of x or log of x, and typically when you see this we are talking about the natural log here. And so here are just some general characteristics of the natural logarithmic function for you, so I'll let you read those on your own. And then here's just a plot of what the natural log function looks like. So when looking at this plot, we can see why this transformation can be useful. And so the reason it's useful is small values that are close together, what the logarithmic transformation does is it spreads them further out, and large values that are spread out are brought closer together. So let's look at taking a log transformation of that example we just looked at. So what we're going to do is we're going to take a log transform of time. And so, for example, if we just looked at that first observation, here is what we have. So the first time point was 1, so then of course log time is going to be 0. So that now that we've transformed the predictor variables, let's see if it helped correct the nonlinear trend in the data. And we can refit the model with prop as the response and ln time is the predictor. So here is our new scatter plot, and we can see very clearly now that the points follow a linear trend. So this looks much, much better than our original scatter plot. And in fact, if you went through and you actually calculated the r-squared of the original model was only 57%, whereas this new one is 99%. So this tells us that 99% of the observed variability in proportional recalled words is reduced by taking into account the natural log of time. And so there should be the word observed variation there. And so if we look here, our residuals versus fitted, that looks much better, and I'll make another comment here in just a minute. Now it is appropriate to look at that normal QQ plot, and we can see here we do have, something that, isn't violating that normality assumption, so that looks really good. Sorry about that. Now the one thing we don't have here is, in order to check heteroscedasticity, we really would want a plot of the residuals versus log time here. So we would want to make sure that we also checked that. But by making this transformation, again, we have seen a huge improvement in terms of linearity, and the normality still looks good. Now one thing to kind of keep in mind here, and this is really going to be true of all diagnostic plots that you look at, is remember, do not overinterpret the plots. Never in real data analysis are you going to see perfect plots. That is just not going to happen. And so, for example, if you look at this residual versus fitted, you might be tempted to say, well, there's a little bit of an up and a down cycle trend on that plot. That doesn't look completely random. But this is a really small data set. I am not overly concerned here. And notice that we've made huge improvements in terms of looking to see if something looks random or not, going from our first one, which looked like this, to this one right here. So again, just be really careful, don't overinterpret the plots. And that includes when, we originally fit this simple linear regression model and we hadn't transformed the variables yet. If you just have slight deviations there, especially with small data sets, don't be overly concerned. But in this case, it was obvious that scatter plot was not linear. All right, so what are some other transformations that you could take? There are lots of other ones. You can do higher order terms like x squared, and you saw those in the linear regression course. And so a question that often gets asked is if we start including terms like x squared and the ln of x, is our model still linear? Because, we were talking about linear models here. And so remember that our focus is always going to be on the parameters. So when we talk about a linear model, we're not talking about, if we've placed, if we've used a transformation on our predictors. We're always talking about linear with respect to the parameters. So just always keep that in mind. So that was a little bit about transforming the predictor variable. Now let's switch over and talk about transforming the response variable. And again, we're going to talk about this for simple linear regression, but you could also do this with multiple linear regression. So before, when we talked about transforming the predictor variable, the reason that we transformed the predictor variable was when we have violated linearity. Transforming the y value is considered when you've got non-normality or unequal variances. So notice transforming the predictor variable, transforming the response variable helps us in ways different than when we transform the predictor variable. And so if you have multiple problems, if you've violated linearity, you have violated non-normality, you might find that you need to transform both. So I'm not going to do that here, I'm doing them separately, but do know that you could do them, both of them. All right, so frequently non-normality and unequal variance departures in the simple linear regression model take the form of increasing skewness and increasing variability of the distribution of the error terms as the mean response, the expected value of y, increases. So for example here, and this is a common one that you would see, is in the regression of length of hospital stay as a function of age, there's going to tend to be more variation and greater positive skewness, and in other words, some really long hospital stays for older adults compared to younger adults. We typically think of younger adults, if we're going to think of how long they're going to be in the hospital, they're probably going to bounce back a lot quicker than an older adult in the hospital. So in those older adults, you're going to see a lot more variability compared to younger adults, so you get your homoscedasticity, and then you're also, you might have some non-normality problems there in terms of your errors. So let's look at a different example. While the ozone layer in the upper atmosphere is beneficial and protects us from ultraviolet light, in the lower atmosphere, it's a pollutant that can be linked to a number of respiratory diseases, as well as heart attacks and premature death. The EPA's national air quality standard for ozone concentration is 75 parts per billion. In Europe, the standard is 60 parts per billion, and according to some studies, at-risk individuals may adversely affect ozone levels as low as 40 parts per billion. So there's a extra zero there. Ozone concentrations, however, are not constant and fluctuate quite a bit from day to day, depending on many factors. And so there is a data set available for you on Canvas. It's the ozone data set. And here are some of the variables in that data set. So we're just going to look at ozone concentration to be the outcome variable, and the rest is explanatory variables. If you were going to visualize a multivariate relationship, you've seen these before, but it's always good to mention here. You can always look at those pairwise comparisons and those scatter plots by using a matrix like this. And so you can see here along the diagonal, you have a histogram of each of the different variables, and then you have the corresponding scatter plots comparing each of them pairwise. So one thing to notice is, for example, these two scatter plots are both comparing ozone and solar. The only difference is which one is on the x and which one is on the y-axis. And so we can see, just kind of looking at the pattern here, that these really are the same data. They've just been rotated depending on which one is on the x and which one is on the y. So here, let's let yi represent ozone concentration on day I, and xi1 represent solar radiation on day I, xi2 represent wind speed on day 1, and so on. And so here, I said we were going to look at simple linear regression. We're actually, I forgot, going to look at a multiple one here. So notice we do have a multiple regression model here where we have 4 different explanatory variables. So previously we saw how to create confidence and prediction intervals. So let's create confidence intervals for 2 hypothetical days. So here are some potential values for day A and day B. And we can fit a model and find those corresponding confidence intervals. It says the following code. I'm going to change that. The code's actually going to be at the end of these notes. So the estimated mean ozone concentration with the corresponding confidence intervals of these 2 days are given here. So notice that things look reasonable for day A, but for day B, our model suggests that the average ozone concentrations may be negative, which is a pretty unreasonable conclusion. And this can happen sometimes. If you go and you make a confidence interval, you may end up with unreasonable values. So one way to fix this is to consider a transformation of the response. So we just, read that the response, or probably transforming the response, can help us when we have non-normality or we have violated heteroscedasticity. It can also help in scenarios like this. So here we're going to model log y. And so just similar to what we did when we transformed the predictor variable, what you would do is in your data set, you would transform your response variable, refit your models, and find your new confidence intervals. And so notice here, we have our confidence intervals. Now these are all going to be on the log scale. And then you can back transform them using the anti-log. And here are our new confidence intervals. And notice these are now all positive. Now, you might say, well, wait a minute here. Is that really valid? And it ends up that it is valid, but we have to be very careful when it comes to the interpretations. Oops. Okay. So remember that previously in the linear regression course, we looked at prediction and confidence intervals. Well, doing that transformation with prediction intervals is fine. And the reason for this is our regression model is used to predict the natural log of y. For, in this case, a prediction interval will be for a single days, not the average of days, because it's a prediction interval. So when you go and you take the predictive value and take the anti-log, you are going to get back y hat. So the transformation of the endpoints of a prediction interval are fine, and it retains its usual interpretation that you would have. However, we do have to be really careful when we use this trick with confidence intervals because the interpretation now changes. And so let's talk a little bit about why that interpretation here is going to change. All right. So remember that when you create a confidence interval, you are trying to estimate the expected value of y. And so let's look at what's happening with this transformation. So let's say you apply the transformation and you look at it and you get normality. So, or at the very least a symmetric distribution. Then the mean and the median of Ly, which is, remember, the thing that you're predicting when you first make the transformation, are going to be the same because it's a symmetric distribution. Using this interval, you can predict the mean or the median of log y. So that's perfectly fine. So what I'm referring to here would be the values in this first table. But when you exponentiate back to get the table that followed that, it's no longer a predicted mean of y, but it's the predicted median. And the reason for this is when you do the back transformation, the median, since it's based on order, it's going to stay in the same spot. But the mean is not going to exhibit that property. And so let's look at another explanation of why this occurs. So if, again, we're thinking of this table right here, the confidence interval from the log data estimates the mean of the log transform data. So in other words, what we are estimating here is the mean of the log data. Now we have this logarithmic property that says if you take the log of x plus the log of y, that's equal to the log of x times y. So applying that, we get this right here. So really what I've done is I've changed that summation into a product here. But we also have the property that the log of x to the a is equal to, and I'll fix this in the notes, that should be a times the log of x. We have the following. This piece right here is what is known as the geometric mean. So really, and by this piece I mean the inside here, so really the confidence interval from the log data is estimating the log of the geometric mean. So when you exponentiate both endpoints of that confidence interval, what you're really getting is a confidence interval for the geometric mean, not the usual mean that we think of. So if you're going to interpret that back transformed confidence interval, your interpretation isn't exactly the same as it was before. It now has to be in terms of the geometric mean. Now, since, a lot of people are like, well, I don't know what the geometric mean is, it ends up that the geometric mean is sometimes an estimate for the median on the original scale. So when we interpret this back transform confidence interval, we want to be careful and not interpret it in terms of the mean, but interpret it in terms of the median. And so, again, technically it's the geometric mean, but that's an estimate for the median. Most people know what a median is. So when we interpret those, we want to make sure we do it in terms of the median. And so the logarithm is the only nonlinear transformation that produces a result that can be cleanly expressed in terms of the original data. And so notice here, I'm saying this, also with the interpretation, because we just need to switch the interpretation over to the median. But other transformations like the square root are sometimes used, but it's more difficult to restate the results in terms of the original data. And then also their corresponding interpretations would be much more messy. So of course, I just showed an example where our confidence interval ended up outside of the range of what we would normally expect, so we use that transformation to help with that. But just like we said at the beginning, when we introduce this type of transformation, it can also help when the normality assumption is violated. And so here, in addition to avoiding estimates that fall outside the logical range of the parameter space, such as transforming, can cause the response to appear more normally distributed. And so here is an example here. So you'll notice we have ozone. That's what it looked like originally. Here we have log ozone, and it looks much, much more normal. You can also add on a constant, and so at times it may be desirable to introduce that constant into a transformation of y, such as when y might be negative. For example, a logarithmic transformation to shift the origin in y and make all y observations positive would be as follows. And so you can see that here. All right. So that is pretty much it on transformations. There is a note here. Another thing that we can do is fit a more flexible model or a more complicated model, but still sticking with linear regression. And some of these you have seen in the linear regression course. So things like adding an interaction term, adding nonlinear functions of explanatory variables, adding in more explanatory variables in the model. But as always, we want to always take care whenever we do anything like this. And then I've got a little note for you here to read about some of those cautions. And then here at the end, I have all the supplemental code for both R and in SAS for any of the calculations that were done earlier in the notes.